Okay, so welcome back, grade 11s and 12s. I hope you guys had a good weekend. So we are just finishing up reactions this week. We just have a couple lectures left, and we'll be all done in reactions. So today's topic is mostly about will the reaction happen? So what you did last week, I find the most difficult part of this whole reactions unit is being able to predict the reactions, predict the products. These last two I don't feel are as difficult as the last task. And this is more focusing around will they happen. You already know now if they are going to happen, how you can predict them, and that's the hard part. But this part today is going to be, well, will they actually happen? Okay, predicting if a reaction will occur or not. Okay, so last week should have been a little bit challenging predicting the products of reactions. Okay, going through and saying, okay, like if I look over here to my picture over the right, if I have Mg and O, what is that going to make? Okay, and if I have H2O2 and it breaks apart, what's it going to make? Okay, and then predicting all the products of these different reactions. We didn't do a neutralization reaction, so don't worry about the neutralization reaction. We'll do those a little bit later on. But these four, okay, being able to predict the products, that should have been a little bit challenging. Okay, so if you found it a little bit difficult, I mean, I looked through your learning checks and I'll be getting those marked back by Friday, but they look pretty decent. Okay, there's a few errors, but nothing major. Now this week should be easier, assuming that you can predict those products. Okay, now that you've been able to determine the reaction will happen in the first place and produce the products you predicted. So today's lecture will go through each reaction type, combustion, synthesis, all the different reaction types, and teach you to predict not only what the products could potentially be, because you already know that, it's if the reaction will happen or not. Okay, and it really kind of revolves around energy and then reactivity. So the first one is combustion. We'll talk about combustion reactions. So when we talk about combustion reactions, it should be obvious to you that combustion reactions don't just happen when you put oxygen and, say, a carbon-based compound together. Okay. Otherwise, just paper being on the table, whenever it touched an oxygen molecule, it would burst into flames, and that doesn't happen. Okay, we don't always have these combustion reactions. Okay, even though these two reactants, like say, even if I take some natural gas and I just open up a natural gas valve and let it be exposed to oxygen, it's not going to start burning. Okay, even though the natural gas is there and it's touching oxygen molecules. Well, why isn't this reaction happening? Okay, we know it can happen, but why isn't it happening? Okay. A very similar example is to say you have gasoline. Okay, gasoline, if you spill it on the ground and it touches oxygen, it doesn't just burst into flames. Okay, all these things that I have on your paper, natural gas, plastic, just burst into flames if they were exposed to air or oxygen. Okay? So it doesn't happen. Well, the reason for it is because in order for a reaction to occur, it needs to be initiated by a little bit of energy. You need to have a little bit of energy to basically rip apart all these molecules. Okay? If you look at it, what a reaction is you basically rip apart the molecules and then reassemble them. Well, in most reactions, it requires just a little bit of input energy to actually do the first rip. So the first ripping apart of CH4, ripping off the hydrogens, and then ripping those oxygens apart, you need to give it a little bit of energy to start. Now, with combustion reactions, you only need to give it that energy once. Okay, you just need to start the reaction, and once it starts, it contains enough energy that it will just keep it going. Okay, so with combustion reactions, you need a little bit of energy to get that started. Okay, and then once you have it started, it will just release energy and release energy and release energy. All right, so getting back here. So in order for a reaction to occur, oops, just get my highlighter out here. So in order for a reaction to occur, it needs to be initiated by an energy in the form of a spark or a heat. So that's what a lighter is. Okay, a lighter is going to release, say, butane gas. There's oxygen there. It's not going to react until you hit that flint or you hit that spark, and that's the energy required to get that reaction going. You don't need to keep hitting the flint, though. You don't need to keep sparking it. Once you started the fire, then the fire has enough energy to keep itself going. So combustion reactions only need a little bit of input energy at the start, but not continuous energy. So therefore, you need to have oxygen, the carbon-based compound, and an initial energy source to start the reaction. From there, the reaction will proceed without an energy source. Now, common energy sources are things like sparks or heat. So most times when we think of, well, how are you going to start a fire? You think of, well, I'm going to use a present fire, like using a lighter or a match, which is already a fire, and then creating a bigger fire. But another way that's sometimes not as known is that things can auto-ignite. So without even having a flame, if I just get gasoline hot enough, if I bring it up to 280 degrees Celsius, gasoline will just burst into flames. It won't need an actual spark, or I won't need another flame to touch it. It will simply just burst into flames. And most substances, especially combustible substances, have an auto ignition point where they don't actually need the spark. It will, just because of the heat, the heat is enough energy to rip apart those molecules and get the reaction going. So just a kind of a quick story I'll tell you about when I was in high school, or just about to go into high school. So I was grade 8, about to go into high school at John McGregor, and part of John McGregor blew up just before going in there. So we were delayed about, I think it was 2 months, where we couldn't go into a certain area of the school. I think we were only 2 weeks from going into the school, and then it was about 2 months from going into a certain area. And how it blew up was basically, the auto teacher had basically taken a bunch of rags that were soaked in grease. Okay, so probably diesel rags. Well, diesel is a combustible. Okay, it can burn. So he had all these rags that were soaked in a combustible, and he put it in a pail. Well, this is in the summertime, and unfortunately, where he placed that pail was where sunlight was shining through a window. So what had happened was the sun shined through the window onto that pail, and over time, on a really, really hot day, got that pail hot enough that it burst into flames without even having a spark there. Well, that pail was right beside another, a bunch of acetylene gas tubes for welding, which caused them to explode and created a small explosion. Okay, so just kind of a story that you don't actually need a spark to start a flame. Also, people who cook, if you ever cook with oils, if you get your oil too hot, it can burst into flames without actually touching a flame. I wanted to go over was a synthesis. Okay, so those are combustion reactions. Okay. The next reaction. Okay, so synthesis reactions can proceed on their own without any input of energy, but most times require a small input of energy at the start. Okay. So placing two elements together will react to form a compound, but normally require small amounts of continuous energy. Okay? So what I mean by this is, with a synthesis reaction, okay, you need to constantly providing it with energy in order for it to keep going. Okay? If you stop giving it energy, the reaction stops. It's a reaction, if you look over here in the reaction things, that requires energy. So this reaction will proceed. I can take oxygen and hydrogen and turn it into water. The problem is I have to be constantly feeding it energy in order to do it. Okay? As soon as I remove that energy, the reaction stops. It's not like that with combustion. With combustion, yeah, you needed to initially give it a little bit of energy, but then you don't need to anymore. It does it on its own. It's different in synthesis. Synthesis, you need to be able to give it continuous energy. Otherwise, it stops. So placing an element and a polyatomic together will also form a more complicated compound with a small amount of constant energy supplied. So I can take something like magnesium, okay, which is the element, combine it with hydroxide, which is a polyatomic. So I'll just kind of, that's what I'm doing over here. So I can take magnesium, combine it with a polyatomic. But if I just put these two things together, nothing's going to happen. If I just take magnesium metal and throw it with some hydroxide, nothing will happen. But if I start giving it energy, okay, and continuous energy, then a reaction will proceed. Okay, but it needs continuous energy, unlike combustion. Okay. So generally, simple synthesis reactions require a constant flow of energy and are known as what we call endothermic reactions, because they basically absorb energy. They keep requiring energy in order to have them going. Okay, so that's synthesis reactions. Now, decompositions are going to be the exact opposite. So decomposition reactions normally do not take place, as a compound is more stable and its elements are not. So normally water is not going to break apart into hydrogen and oxygen gas, okay, because the elements are too unstable, hydrogen and oxygen. They would just want to form together and go back into a compound. So if a decomposition reaction is forced to take place, you do need to provide it a small amount of energy at the start, just like all reactions. So all reactions require at least energy at the start. Just with synthesis, you need to keep giving it energy. Okay, but with decomposition, it's like a combustion. It doesn't require it after the initial jot of energy. So the reaction itself will produce amounts of energy afterwards. So a decomposition is the opposite of a synthesis reaction. So if we look at a synthesis reaction, okay, you're going to have H2 plus O2. You have to put a little bit of energy in, and then you're going to get H2O. Okay, but that's it. That's all you're going to get is H2O. Now with decomposition, it's a little bit different. You're going to take water, add a little bit of energy, right? It's going to break apart into H2 and O2, but you also get energy out. Right? It's known as what we call an exothermic reaction, which would release energy. All right, that's decomposition. So just in summary of the three, right? If we look at all three and talk about them, combustion reactions will only happen if a small input of energy is initially supplied, then it will release energy on its own. Okay? And release large amounts of energy. In a synthesis, reactions require a constant feed of energy to keep them going, and no energy is released. Okay? And then my last one is decomposition. The reaction requires a small input of energy originally, but similar to combustion, releases energy afterwards. Okay? And that's really kind of the next lecture is going to give you kind of real-life examples of when this is happening. But those are the first three. Now we have one more that we're going to go through, which is single displacement. Okay? So, single displacement reactions. Okay? Unlike the first three reactions that primarily revolved around energy if the reaction is going to happen or not, single displacement reactions revolve around reactivity. I mean, they all revolve somewhat around energy, but this one's going to be more focused around reactivity, determining whether something's going to happen or not. So recall, when we look at a single displacement reaction, it's going to be an element plus an ionic compound, and if it's going to actually happen, it's going to produce an element in an ionic compound. Okay? So an example that I have down here is we've got an element here. Okay, I've got my elements here, and then I've got my compounds, which I'll do here in red. Okay, and if this was actually going to happen, we could finish this, we'd say, okay, well, this is positive, positive, that's positive, and then I'll do my negatives, that's negative, negative, negative. So if I was to predict this, and this is kind of what we were doing last week, I would say, okay, the two positives are going to switch, and I have to do my crisscross rule, so I'm going to get MgCl2 plus, and that's going to leave sodium on its own. And the bottom one, I look and say, okay, well, this one's going to have the two negatives are going to switch, so I'm going to get NaCl plus F2 on its own. Okay. Now, this is the main idea in these reactions. Okay, so that was just kind of a recap of what we did last week. So this is the main idea. We have to now predict, well, will this actually happen? Are these products going to be made? Are they or aren't they? Okay. So this is the main idea of how you know whether the reaction will happen or not. Reactions will only occur if the element reactant, so the element reactant here is the magnesium and the chlorine. So the element reactant is more reactive than its counterpart in the ionic compound. What I mean by its counterpart, so if you look at chlorine, it's a negative or a non-metal. Its counterpart is fluorine. Okay? If we look over here at magnesium, it's a positive or a metal. Its counterpart is the other metal, sodium. Right? So the reaction will only proceed if the element reactant, chlorine or magnesium, is more reactive than its counterpart in the compound. So is chlorine more reactive than fluorine? Okay? Or is magnesium more reactive than sodium? Okay? The reaction will only proceed if it makes the most reactive element into a compound. If the most reactive element is already in a compound, the reaction will not proceed. So when we look at this, okay, and I'll give you some examples when we come up. So let's go to the next slides because we'll kind of clarify this. So this is the main idea. Okay, I'm just going to highlight this again. Okay, so let's go through these reactions. Now again, when we do our single displacement, some of you don't need to do this, but I like to do it because it limits the number of mistakes that I make, is I'm going to match all these up. So that's a metal, that's a metal, 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 and metal. And then I'll do all my non-metals, negative, 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 and the oxygen's negative. Okay, now I do that just so I know who's switching with who. So now what I have to do is I have to say, okay, I look at this example. So I look at this example and I have to figure out, well, this reaction right here. So let's take a look at my first example here. I'm going to highlight this. So this reaction right here. This reaction will only occur if It says right here. The reaction will only proceed if it makes the most reactive element into a compound. So I look at all these different elements and I say, well, the most reactive element has to be in the compound. Okay? Now, the only two things that can switch right here are magnesium and iron. So I have to make sure between magnesium and iron, which one is more reactive. If it's magnesium, then I need to switch them. But if it's iron, then I just leave them and there's not going to be a reaction. Okay? Then I say take a look over at this one right here. Right? And the options that I have here is that sodium and lithium could potentially switch if the reaction is going to happen. But I have to make sure the reaction will only proceed if it makes the most reactive element into a compound. Well, I have to figure out, well, who's more reactive, sodium or lithium? If lithium is, it's already in the compound and no reaction. But if sodium's more reactive, then I have to switch these things in order to make sodium the most reactive element in a compound. Now, it's the same kind of thing when we go down here, but this is now with gases. I take a look and I say, okay, well, I've got fluorine gas and chlorine gas. Okay? These are the two gases that I have. Now, which one is more reactive? If it's chlorine, great. It's already in a compound. I don't need to do anything. But if it's fluorine, then I'm going to have to switch them, right, in order to make sure that the most reactive element, fluorine, is in the compound. Over here, the same thing. I look at bromine and reacting with sodium fluoride and say, okay, well, bromine and fluorine can potentially switch, but which one's the most reactive? Right? So I keep saying, well, which one's the most reactive? Which one's the most reactive? Well, how do you go? Okay, well, we use a chart. So we're going to give you this chart always, okay? You always would have this activity series. You don't have to memorize it. And basically, this is the idea of the chart, is we have the most reactive up at the top, and down at the bottom, we have the least reactive. Okay, and you can see things like gold and platinum that are very, very unreactive are right down here at the bottom. And things that we know are reactive, things like lithium and potassium and sodium are high at the chart. Okay. So this is basically how we go about doing these questions and predicting if the reaction is going to happen. Well, the first thing I'm going to do is I'm going to do my positives and negatives again. Okay. And I go back, do my negatives now. Oxygen negative, fluorine negative, chlorine negative. And the negatives I'm just referring to are nonmetals because they form negative ions and metals form positive ions. Okay. So we take a look at our first reaction. Now, I know you could say, well, I know how to finish this. I'm going to have magnesium and iron are going to switch and it's going to make MgO. Okay. But we have to see if the reaction is going to happen. So what I do is I say, okay, what are the two things that could potentially switch, magnesium and iron? So then I look over here at the reactivity chart and I say, well, here's magnesium and here's iron. So when I look at it, I say magnesium is more reactive than iron because it's higher up the chart. It's closer to the most reactive. So because magnesium is more reactive than iron, I need to get magnesium into that compound. So in this case, the reaction is going to proceed. I have to get magnesium into the compound. I need to turn it to, well, there's a better color here, MgO. I did my crisscross rule, so there's my formula. Now it's in compound mode, and the less reactive metal is in element mode. Okay? So whatever's the least reactive, whatever's on the bottom of this list has to be on its own, and the most reactive, it's got to be in a compound. Okay? Now we take a look over here at my second example. So my second example, let me just quickly erase this. So I take a look at my second example, and now I have fluorine combining with sodium and chlorine. Well, I can see that I have two negatives in this one. So my fluorine and chlorine can potentially mix. So I look over here and say, well, there's chlorine. It's at the very top, and fluorine is just below it. So the most reactive is chlorine. So if I look over here, I need to make sure chlorine is in a compound. Well, it already is. Right? So because chlorine is more reactive than fluorine, we say no reaction. Now, you may be saying, well, you told us before that fluorine is the most reactive element. It is as an overall picture in terms of all the different things that it can react with. But when we're talking about it reacting with an ionic compound, there is chlorine that happens to be a little bit more reactive than fluorine. Okay, now we look down at my next example here. Okay. And I've got bromine and sodium fluoride. So I look over and I say, okay, well, here's bromine right here, and fluorine is just above it. So I need to have my most reactive element in compound mode. My most reactive between bromine and fluorine is fluorine. So again, no reaction here. Nothing's going to happen. Okay. I look at my bottom one here. And let me just erase kind of what I have over here. So if we look at my bottom example, where I have sodium reacting with lithium chloride. We say, well, sodium and lithium can potentially mix. Where is sodium and lithium? Well, sodium is right here, and lithium is right here. So we need lithium in the compound. It is the most reactive. And it happens to already be in the compound because it's the most reactive, and we can say no reaction. Okay. So you're really kind of just using this chart and deciding, if the most reactive is already in compound, nothing happens, like in these three cases. However, if the element on its own is more reactive, then you have to do the reaction like you were doing before. Okay. Now, there's nothing for predicting double displacement reactions. It's going to be covered when we do our solutions unit. So that's everything on predicting reactions. I know it was a longer one. Our next lecture is going to be shorter.